So what I have done is that I have shown the cross-sectional view of a say of a round rotor, or you can call it to be cylindrical rotor. You can also call it to be non-salient pole rotor. So it's a cross-sectional view of a two-pole synchronous machine. Field winding is placed on the rotor, and armature winding is placed on the stator core. And we usually give DC supply to the field winding with the help of two brushes and slip rings, which are connected to the positive and negative terminal of the DC supply. So the field winding is housed on the rotor, and the two ends of the field winding is connected to slip rings, and these slip rings are mounted on the shaft, but they are insulated from the shaft. And on the slip rings we have two brushes, and those brushes are pressing on the slip rings, and those brushes are having lead of wire embedded inside them, and those leads of wire are taken out to the terminal box where we can connect a source of DC supply. So this thing I have shown you the schematic way in my earlier lecture. So just it's a recap. So now we are giving DC supply. Let's say that let's say we want to form north pole over here, and we want to form south pole over here. So if that is the thing, that we want that this part of the rotor should be your north pole and this part of the rotor should be your south pole. So we can put the dot and cross in this way. First of all, let us indicate the direction of the magnetic lines of flux. Inside the magnet lines of flux are from south to north pole. So this is the direction of the magnetic lines of flux, because it is inside the rotor, and the rotor is the magnet, and we know that inside the magnet lines of flux are from south to north pole. Now you can apply that right hand rule to find the direction of current through the field winding. So you will find that this part of the rotor, they are going to carry cross current. This part will be cross current, and on the left part we have this dot current. So if you just apply that right hand grip rule, you will be able to figure out that the thumb is pointing in upwards direction. If you apply the right hand grip rule, you will find that thumb is pointing in upward direction, and inside the magnet means the rotor is becoming a magnet when the field windings are carrying current. So it is from south to north pole. Now let us further assume that the rotor is being driven by a prime mover, because we have taken alternator. So for alternator means your synchronous generator, and synchronous generator means that input will be mechanical energy, and that input mechanical energy is provided by a prime mover. So prime mover, let us assume that prime mover is driving the rotor in anti-clockwise direction at synchronous speed. So we are showing this by a arrow marking on the rotor, that the rotor is driven by a prime mover, and the prime mover is driving the rotor in anti-clockwise direction at synchronous speed ns. Now regarding the naming of the armature winding or armature coils on the stator core, we take that the phase sequence of the induced EMF in the armature winding, the phase sequence of the induced EMF in the armature winding is ABC. So what is the meaning that phase sequence is ABC? ABC means that first the peak of phase A will happen, then the peak of B is going to happen, but between peak of phase A and between peak of phase B, there should be a time gap of 120 degree. Now what is the meaning of time gap of 120 degree? Actually, to be precise, we know this relationship, that one complete cycle of sinusoidal wave, means an angle of 360 degree electrical. So this 360 degree electrical can be also called to be the time period. But what is time period? Time period is reciprocal of frequency, that is 1 by f. So if you want that the frequency of the induced EMF in the armature winding to be 5050 Hz, you want that the induced EMF frequency in the armature winding should be 50 Hz. So in that case, your F will be 50. Of course, you have to drive the rotor in that speed. So if you just simplify this, it will come as 20 milliseconds. So 360 degree means 20 milliseconds. So 120 degree means 20 by 3 milliseconds. So when we say that between the time instant when peak is happening in phase A and peak is happening in phase B, there should be a gap of 20 by 3 millisecond, or you can call that 120 degree. So right now in the diagram you can see this north pole of the rotor is in front of this coil side on the armature. Let me write this as coil side A. So I am writing this as coil side A, and this I am writing coil side A dash. So what you can see, north pole and south pole are in front of coil side A and coil side A dash respectively. So this will have the peak induced EMF right now. But the rotor is rotating. So after the rotor has rotated by an angle of 120 degree in the anti-clockwise direction, north pole will come in front of this coil side. So we call this coil side to be coil side B, and this coil side we are calling it to be B dash. Likewise, further if the rotor rotates by 120 degree with respect to this position, when north pole is in front of coil side B, it will come in front of this coil side, which we are calling as coil side C, and here this opposite side is your C dash. So now if you apply that modified Fleming's right hand rule, modified means what? You assume that the rotor is stationary and conductor is moving in a direction opposite to the direction of rotor. So the rotor is moving in anti-clockwise direction. So if I take a point, let me use some another color. Let me use this red color. Let's say I am taking a point on the rotor surface, which is shown by a red dot. So I am taking a point on the rotor surface, which is shown by a red dot. So what is the tangential velocity for this rotor? It is from right to left. That means in this direction. Right to left means it is in this direction. Now what you have to imagine, that the rotor is stationary and the conductor, you have to only imagine, it is not actually happening. But since we want to apply the Fleming's right hand rule, but here the field is moving, so that's why we are modifying it so that we can apply the Fleming's right hand rule. So what you can do now, you imagine that the rotor is stationary and conductor is moving in a direction opposite to the rotor, that means in this direction. So if this is the perceived direction, so in that case if you apply that Fleming's right hand rule, the index finger of the right hand will point upwards, that means from south to north, that means the direction of the magnetic flux density. Let me write to be this your BF. F stands for the field winding, magnetic flux density created by field winding, and velocity is in this direction. So if you apply Fleming's right hand rule, you will find that the induced EMF polarity in this conductor or coil side A will be given by dot. If you apply that, you will find it is given by dot. So I am putting a dot over here. So let me put a dot in this diagram. I am putting a dot over here. Now if you carefully notice, you will find that the coil side B dash and C dash, they are also under the influence of north pole of the rotor. Coil side B dash and coil side C dash, they are also under the influence of north pole of the rotor. So they will also have dot. Of course, the magnitude of induced EMF will be little less compared to coil side A, because coil side A is directly in front of north pole, but otherwise it will also have dot. Now, by the simple logic that conductor under north pole, if it is dot, conductor under south pole will be cross, or if you wish, you can again apply that modified Fleming's right hand rule, and you will find it is given by cross. Now this was the basic recapitulation which we have done earlier. Okay, now what I am going to do is, now is that uh, I am trying to make you convinced that although there are three coils in the diagram, coil AA dash is belonging to phase A, coil BB dash is belonging to phase B, coil CC dash is belonging to phase C. So there will be three magnetic axis, or there will be three MMF, that is magnetomotive force MMF axis. But what we will do is that we will take the combined MMF. Combined means the resultant MMF. Resultant MMF means what? Resultant MMF means that the resultant of the MMF for coil AA dash, resultant of the MMF for coil BB dash and coil CC dash. So what we have learned is that the resultant MMF or the resultant magnetic axis is aligned with the magnetic axis of that coil which is carrying the peak current. So at this instant, what you can see in the diagram, at this particular moment, the peak induced EMF is happening in coil AA dash. So peak current will be carried by coil AA dash only. So the resultant MMF or the resultant magnetic axis will be aligned with the magnetic axis of coil AA dash. So we will indicate the armature MMF FA. Now please note that when we are saying FA, so here A is standing for the armature winding. A is standing for armature winding. A does not stand for phase A. A stands for armature winding. So the resultant MMF of the armature winding, or the simply armature MMF, will be aligned with the magnetic axis of coil AA dash, because coil AA dash will carry the peak current. Why coil AA dash will carry the peak current? Because induced EMF is maximum in coil AA dash. But yes, it is also true. What is true? That after some time, when the rotor has rotated by 120 degree in anti-clockwise direction, after some time, when the rotor has rotated by 120 degree in anti-clockwise direction, what will happen? Peak of coil BB dash will happen, and in that case the armature MMF will be aligned with the magnetic axis of coil BB dash. Likewise, 120 degree further rotation of the rotor will make the induced EMF maximum in coil CC dash. In that case, the resultant MMF, that is the armature MMF, will be aligned with the magnetic axis of coil CC dash. So in that way, we have to visualize that armature MMF FA is also rotating, but at what speed it is rotating? It is rotating at synchronous speed, that is ns, and we are calling this by FA. A stands for armature, and FA is also rotating at synchronous speed. Okay. Now, what do you find? That reluctance which is offered to the field MMF and armature MMF both are same, because the air gap is uniform. Air gap is uniform between the rotor and stator, isn't it? Air gap is uniform, so they are offered the same reluctance. For example, if I say this is my FF means field MMF, and this is FA, the armature MMF. So what we can write? Let me write it because it is important point. What I am saying is that reluctance offered to field MMF, that is FF, and armature MMF, that is FA, are same, because the air gap is same for both of them. So that's why we have actually written this equation. Let me write it, and this will be some sort of recap for you. What we have written earlier, that FR, that is the resultant MMF, FR, that is the resultant MMF, is going to be given by the phasor sum of field MMF and armature MMF. Phasor sum of field MMF and armature MMF. So this is a phasor sum, so we have to put a bar over this. Now, since FF and FA both are rotating at synchronous speed and in the same direction, that's why the angle between FF and FA, they are not going to change. So we can write this, that since FF and FA both are rotating, both are rotating at speed ns, that is the synchronous speed ns, and in the same direction, and in the same direction, in the same direction. So what can we surmise from here? We can surmise that the angle between ff and fa, the space angle, will not change. The space angle, let me write it, the space angle, the space angle between, the space angle between ff and fa will not change. It will remain constant, will not change. Now let us start the process of drawing the phasor diagram of round rotor alternator. This was your recapitulation, like that, whatever we have done till now. So what is the basic idea of drawing the phasor diagram? Let me express this with this flow chart. What is the flow chart? Is that magnetomotive force, that is MMF, it is leading to the establishment of flux. Flux means the magnetic flux, okay, and flux is going to establish the induced EMF. Flux is going to establish the induced EMF, okay. So this is this sequence or sequel. So keeping in view what we have written here, that FR is given by FF plus FA. So we can rewrite this as air gap flux phi r, or the resultant flux phi r, is equal to field flux phi f plus armature flux phi a. Now further, this will give rise to resultant air gap voltage ER. This will give rise to EF, that is the no load voltage or no load excitation EMF, and this will give rise to let us call this to be EAR, that is EMF induced due to the armature flux. So this is the sequence. You can correlate this thing. Okay. Now what will be given to you for drawing the phasor diagram? What are the given quantities? Let me write it. Given quantities. Given quantities. What are the given quantities? First is the per phase terminal voltage, load power factor angle theta, armature current IA. So these are the things given. What else is given? Per phase armature winding resistance and armature leakage reactance XAL. So this armature leakage reactance, just let me indicate it over here. Let me just copy this so that we can use it somewhere else. So what is your leakage flux? Actually leakage flux are those flux which is only linking the armature conductors. For example, if I just indicate this leakage flux, so this can be termed as your leakage flux, this can be termed as the leakage flux, this can be termed as the leakage flux. That means what do you find? That the leakage flux is linking the armature conductors only. So these will be termed as armature leakage flux. These are known as armature leakage flux. So armature leakage flux are linking only the armature conductors. Okay. So they will give rise to induced EMF, and that induced EMF, so let me write it, armature leakage flux will give rise to induced EMF. induced EMF in armature winding, and this will oppose the no load EMF. No load, it will oppose, okay, it will oppose no load induced EMF, which is indicated by EF. So what is done, this effect that EMF induced due to armature leakage flux is going to oppose EF, that is no load induced EMF. This effect is modeled by or represented by voltage drop in a fictitious reactance which is known as armature leakage reactance, that is XAL. So what are the things which are provided? Let me take you what are the things which are provided. The given quantities are the per phase armature terminal voltage, that is Vt, load power factor angle theta, because it's an alternator, that is synchronous generator, so it load will be electrical load, so that electrical load will have some power factor, so that is your theta. Theta is the load power factor angle, theta is the load power factor angle, the load which is connected across the armature terminals. Ia is the armature current per phase, Ra is the armature winding resistance per phase, XAL is the leakage reactance of the armature winding or armature winding leakage reactance. So these things are given. So how to proceed drawing the phasor diagram? So let me start with, so what we are going to do is that first we will draw the terminal voltage Vt. Okay, so first thing is that we will draw the terminal voltage Vt. So I am drawing the terminal voltage Vt over here. So this is the terminal voltage Vt which we have drawn. Now this is my Vt. Now let us assume that the alternator is operating at a lagging power factor. So if it is operating at lagging power factor, that means the load, the electrical load which is connected across the armature terminals of the synchronous generator, that load is lagging power factor load. So armature current is going to lag the terminal voltage Vt by some angle, which is the load power factor angle theta. So say armature current Ia is lagging the terminal voltage Vt by load power factor angle theta. Now what can we do? We can add armature resistive drop and armature leakage reactance drop so as to get the air gap voltage, that is ER. Okay, so I am writing here in the equation form first, then I am drawing. What I am saying is that in order to obtain the air gap voltage ER, you have to take the phasor sum of the terminal voltage Vt plus the armature resistive drop, that is IARA drop, plus the armature leakage reactance drop. So these things, this equation will guide you that how can you obtain the air gap voltage, how can you obtain the air gap voltage ER. So you can obtain the air gap voltage ER by adding armature resistive drop, that is IARA drop, and armature leakage reactance drop with the terminal voltage Vt. So let us draw that. So first we will draw the armature resistive drop or the ohmic drop in the armature winding. Since it is ohmic drop or the armature resistive drop, so it will be in phase with armature current. So that's why this IARA drop will be parallel to the armature current Ia, like this. So it is parallel like this. Now the IAXAL drop, that is the armature leakage reactance drop, will be in quadrature with the armature current. So it will be shown like this. So this is your armature leakage reactance drop. So I can actually indicate this by extrapolating this one. Let me use this one. Let me show you. You can view it over here, that this IA Excel drop, you can view it here like this. You see, it is your in quadrature, isn't it? It is in quadrature. So you can just make it dotted like this. So this is your IA Excel drop, this thing. This is your IA into XAL drop. This is your IARA drop, that is the armature resistive drop, IARA drop, IAXL drop. Now, if you go by this equation, then you can simply find what is your air gap voltage ER. This is our air gap voltage ER. Let me rewrite this terminal voltage VT. So this is my terminal voltage VT per phase, armature terminal voltage, and this is my air gap voltage ER. Now, due to armature current IA, there will be a armature flux phi A. It has to be, because there is armature MMF due to armature current. So there will be a armature flux phi A also. So you have armature flux phi A established due to armature MMF FA. So armature MMF is FA, and it is going to establish armature flux phi A, isn't it? So this is my phi A. Now, if I ask, or rather if we think simply, that what is the nature of the induced EMF in the armature winding? So it has to be statically induced EMF, no doubt in that, because of the simple reason that the armature windings are stationary, because they are on the stator core. The armature winding is on the stator core, so they has to be stationary. But EMF is induced in the armature winding, so that means it is statically induced EMF. So it will be actually like transformer EMF, and induced EMF due to the fluxes in the armature winding will be lagging by 90 degrees. So if we call that this is our armature flux phi A, let me write over here, let's say this is your phi A. So the induced EMF due to this is going to lag by 90 degree, isn't it? So it will be lagging by 90 degree, means like this. Let me show it over here. So this thing is nothing but it is your EAR, that is EMF induced due to armature flux. Now, this induced EMF in the armature winding due to EAR, what is EAR? EMF induced due to armature flux phi A. So it is the EMF induced due to armature flux phi A. So this is also going to oppose the no load EMF EF. So we are going to model this by a voltage drop in a fictitious reactance, which is known as armature reaction reactance. Like let me write it first. XAR, it is actually known by the name of armature reaction reactance. Armature reaction reactance. So this is your XAR. So let me indicate it over here like this. This is your shown by this drop in a fictitious reactance. Now one thing I would like to mention, please take a note of this, is that in this diagram this IAXL drop is exaggerated. Exaggerated means it is shown much larger than the actual value. This voltage drop, let me write it over here, this voltage drop is exaggerated. Exaggerated means that it is shown larger than actual value. It is shown larger than actual value. So in a real machine, in a practical machine, this drop IEXL drop will be very small. Okay, I must admit this. So that's why I have written this comment. This voltage drop is exaggerated. It is shown, it's shown larger than actual value. Okay, so now this is your IAXAR drop. This thing is your J. Let me. This thing is your J into IA into XAR drop. Okay. Now, if we go by this particular equation, that what was the air gap voltage? Let me write it over here only once more. Let me write it once more. That air gap voltage ER equals to EF plus EAR. If you go backwards, then this is due to the resultant air gap flux. This is due to the field flux phi F. Okay, this is due to the armature flux phi A. Okay, so if you go by that, so we can actually find out what will be your EF. Okay, so let me indicate this EF. This thing is your EF. This thing is your EF. Now, what is the relationship between flux and induced EMF? The relationship between flux and induced EMF is that of 90 degree. 90 degree why? Because as I have said, again I am saying that the EMF induced in the armature winding is statically induced EMF or transformer EMF. Because of the simple reason, armature windings are placed in the stator core. Stator core is stationary. So whatever EMF is induced in the armature winding, it has to be statically induced EMF or transformer EMF. Now in a transformer, you know that the flux is leading the induced EMF by 90 degree, or you can call it in the reverse way, that the induced EMF due to a flux, the induced EMF due to a flux will lag the flux by 90 degree. So accordingly, where should be your FF, where should be your FA? This thing we can indicate it over here. Let me indicate it. So FF will be leading by 90 degree. So this thing is your FF. Now what about phi R? Phi R will be leading the resultant air gap voltage ER by 90 degree. So this will be your phi R. Let me write it over here. This is you can either call it to be your FR or you can call it to be your phi R. And this thing is your FF, or you can call it to be your phi F. Okay. Now what is FA? FA is this one. Let me show it over here. This thing can be called FA because FA is directly proportional to IA. FA is directly proportional to IA because if armature current is 0, armature MMF is 0. If armature current is maximum, then armature current is maximum. If armature current is maximum, then armature MMF is maximum. So IA, FA are in phase. So this is your FA. So we can indicate this FA by this particular diagram over here. So this thing is your FA. This thing is your FA. So this is the general phasor diagram for a round rotor synchronous generator. Now what do you further you can find it over here is that, let me indicate it, it is important, is that whatever is the angle between FF and FR, this is your FF and FR. So whatever is the angle, that angle has to be same between EF and ER. So these two angles are equal. So if this angle is delta, so this angle will be also delta. Delta is known as the torque angle or the load angle. But actually what happens, let me write it, IARA and this armature leakage reactance drop, IAXL, this drop, this voltage drop is usually very small. This is usually very small. So what can we say? That Vt is approximately equal to ER. Now that's why in some cases or in some textbook the angle between EF and Vt is also sometimes known as delta. Also sometimes called as delta. Why? Because of this particular thing, that this IARA and IXL drop is usually very small. Now the angle between EF and IA, that means this particular angle which I am showing it here, this angle is known by the name of psi. Psi is known as internal power factor angle. Psi is known as internal power factor angle. So this is the actually the general phasor diagram for a round rotor synchronous generator. Now usually in most of the numerical problem of synchronous machine, or if you are solving in particular the numerical problem of synchronous generator, the MMF are not needed that much. This FF, FA, FR, these are usually not needed. So in that case you can omit this MMF part and you can only draw the phasor diagram which is involving the induced EMF, the terminal voltage and the armature current and the drop, various drop, armature leakage reactance drop, armature resistance drop. So I will just draw this phasor diagram once more, but this time I will not draw the MMF part. I will only draw the induced EMF and the terminal voltage and the various voltage drop which is taking place. Okay. So any question you would like to ask up to this point? Anybody? Any question if you have? Okay. Yes, if you sir. Okay. So let me draw the phasor diagram. This is also the phasor diagram of round rotor synchronous generator, no doubt. But here we are also indicating the MMF part. But in most of the numerical problems which is involving synchronous generator, usually the voltage and current phasors are needed. So let me draw once more. So once more I will take up the case of lagging power factor load. That means we will assume that the load which is connected across the armature terminals is lagging power factor load. And what are the things given to us? We are given the following things. What is given to us? Terminal voltage Vt per phase, armature terminal voltage, load power factor angle theta, armature current Ia per phase, armature leakage reactance XAL, and armature resistance per phase, that is Ra. These are the things which are provided to us. Based on this we have to draw the phasor diagram. So we will start with the terminal voltage Vt. So we are starting with the terminal voltage Vt. So this is our terminal voltage Vt. Now according to the problem, the armature is loaded with a lagging power factor load. So armature current Ia is going to lag the terminal voltage Vt by angle theta. So we will indicate this thing by this one. let's say this is your armature current IA, and armature current IA is lagging the armature terminal voltage VT by angle, load power factor angle theta. Now what we will do, we will add up this, let me write this equation once more. What we have written earlier is that air gap voltage ER can be obtained by adding what? By adding the terminal voltage VT with the armature resistive drop, that is IARA drop, plus armature leakage reactance drop, that is IAXAL drop. So let us plot that. So IARA drop will be parallel, since resistive drop is in phase with current. So IARA drop is parallel to IA. So this is my IARA drop. Now this time I will be careful. I will not exaggerate the armature leakage reactance drop, which I have exaggerated earlier. Okay. And to this we will add up the armature leakage reactance drop, this one. So let me write it over. So this thing is your armature leakage reactance drop, IAXAL, and this thing is your armature resistive drop, that is IARA. Now if we add this, then we should get the air gap voltage ER. So let me write that ER. So this is the air gap voltage ER, air gap voltage. Now if you go by this equation, let me write the equation. What was the equation? That air gap voltage ER equals to the no load EMF EF plus EAR, isn't it? So if you go by this, then what you have to do, you have to add EAR, isn't it? So EAR, what you have to do, you have to add means what? First of all, what is EAR? It is produced due to the armature flux phi A, right? Where is the armature flux? Armature flux is in phase with this armature current IA. So this is my armature flux phi A. This is armature flux phi A. So EAR is going to lag na by the flux by 90 degree. So this thing we can indicate it by like this. So this thing is your EAR. But remember, the effect of armature flux, the effect of armature flux is the effect of armature flux is modeled by, the effect of armature flux is modeled by a voltage drop in a fictitious reactance, which is known as armature reaction reactance. What I want to say is that the effect of phi A is modeled by, the effect of phi A is modeled by voltage drop in a fictitious reactance, in a fictitious reactance. What is that fictitious reactance? Named as XAR, which is known as armature reaction reactance. So we are actually indicating this thing by this one. So this thing is your IA into XAR, this voltage drop. Okay. Now if you just add this ER with this, you should get EF. So we will get back our EF, that is a no load EMF. So let us do thing. So this will be your EF. Let me do one thing. Let me just play with this particular equation. Okay, this is important. If you play with this equation, what do you see? Let us play with this equation. If we bring this EAR to the left hand side of the equation, so what is going to be our EF? Let us write it. From this only What is EF? EF equals to ER minus EAR. You can see it over here. EF equals to ER minus EAR. But what is minus EAR? You see, this minus thing, you see the phase of these two quantities are opposite, na? You notice the phase orientation. Notice the phase orientation of EAR and J into and J into IA XAR. They are 180-degree out of phase, isn't it? So that means what? This thing can be equated to minus EAR. We can call this to be minus EAR, no doubt. Okay. So there is no problem in that. If we just add ER and minus ER, we should get back our EF, that is the no load EMF. So this is our no load EMF, EF over here. Okay. So this is our EF. Now what is done is that we have given a special name to the summation of these two reactances, which are fictitious reactances, but the reactances XAR and XAL, they are termed as synchronous reactance. Synchronous reactance. So let me write this with a different color. So what we are going to write, XS, that is the synchronous reactance, equals to nothing but it is the summation of XAR plus the armature leakage reactance, that is XAL, this thing. So XS is known as synchronous reactance. XS, X suffix S, that is XS, is known as synchronous reactance, and it is summation of armature reaction reactance and armature leakage reactance. Okay. So then we can again simply draw this in a neat way. Now this time we will not draw EAR and phi A and all those things. Okay, so let me just draw this phasor diagram only once again, taking into account these things, that the sum of XAL and XAR is known as what? XS. XS means the synchronous reactance. Synchronous reactance. So let me draw it once more. So again we will start with the terminal voltage of the armature winding per phase, that is VT. So this is, we are starting with VT like this. Okay. So this is your VT. We are assuming that lagging power factor load is connected with the armature winding. So armature current will lag the terminal voltage VT by the load power factor angle, theta. Now to this we will add the armature resistance drop, that is IARA drop. Since it is a resistive drop, it will be parallel to the armature current. So this is your IARA drop. Now to this drop we will add this synchronous reactance drop, that means IAXS. Let me show it over here. So this thing is your J into IA into XS. Now what is XS? XS is nothing but it is the summation of XAR plus XAL, armature reaction reactance and armature leakage reactance. Now sum of these two will be obviously the no load EMF, that is EF. So this thing is your EF. Now if you want to find that those things, for example, angle between EF and VT is your given by delta. Delta is the load angle or the torque angle. Angle between EF and IA is indicated by psi. Psi means the internal power factor angle. Psi is what? Internal power factor angle. And this particular thing, let me show it over here. This particular thing is also sometimes known as IAZS. ZS is the synchronous impedance, IAZS, where ZS is what? Synchronous impedance. It is given by RA plus JXS. Okay. So this is the phasor diagram for your lagging power factor load. For unity power factor load, what will be the phasor diagram? Let me draw unity power factor. So again we will start with the terminal voltage Vt as usual. So we are starting with armature terminal voltage Vt here. So we have drawn the armature terminal voltage Vt first, right? Now since we are assuming unity power factor load, so armature current and terminal voltage, they will be in same phase since it is a unity power factor load. So this is our IA, it's a unity power factor load. Now armature resistive drop, that is IARA drop, will be in phase. So this is your IARA drop, this thing is your IARA drop, and IAXS drop will be in quadrature to this because it's a reactive drop. So it is in quadrature to this. So this is your J into IA into XS. Okay. So how to get EF? EF will be the sum of these quantities. So this thing is your EF. And of course phasors are rotating in this anti-clockwise direction at an angular speed of 2 pi f. Okay. Likewise here also you can indicate that phasors are rotating in this anti-clockwise direction at an angular speed of 2 pi f. So this is also thing. So in this case, this is the load power factor. This is the load angle or the torque angle, and this is also the internal power factor angle psi. That means here you can say that delta equals to psi, because psi is known as internal power factor angle. It is known as internal power factor angle. Okay. And delta is the load angle or the torque angle. Delta is the load angle, or it is also sometimes known as torque angle. Torque angle. So this is the phasor diagram for, this is for unity power factor load, for unity power factor load. Of course it is for round rotor synchronous generator. And this one is for, this phasor diagram is for lagging power factor load. This is for lagging power factor load. Okay, so let me indicate this synchronous impedance term, that is IAZS drop. This is your, this thing is your IAZS. IAZS. What is ZS? Synchronous impedance. ZS is synchronous impedance, that is armature resistance RA plus synchronous reactance XS. Okay. So let me stop over here for today. So if you have anything, you can ask me. Any question up to now?